In this video, I want to just briefly talk about comparison test. And comparison test is one that is really useful for knowing if something converges or diverges. And then you may have to, if it converges, you may actually have to do the integral and then find the actual answer. But if it diverges, it could save you some time. Now, I've drawn just a couple of easy graphs here. You can see I've got 1 over x squared, which this is something that on the very first day we looked at and we said, well, this definitely converges. We found that answer as you go to infinity. And then below that, I've graphed 1 over x cubed. And I guess what I'm trying to point out here is that 1 over x squared is such a small function. It hugs the axis so tightly as it goes to infinity that it converges. And 1 over x cubed is even smaller, and you can see that by the graph. It's even smaller than 1 over x squared. So if 1 over x squared converges, and it's greater than 1 over x cubed, that must mean this has to converge as well by just comparing the two. Now, what does it compare to? Well, I'd have to actually find the integral and do it, but it at least gives us an idea that it's worth doing the integral, so we don't go through all the work to find out it diverges. This next example, 1 over x, on the very first day we looked at and we said that this diverges. It's not small enough that we can actually get an answer. And above that I've graphed 1 over x, 1 over the square root of x, which is a larger function. You can see that it's even bigger than 1 over x. So doesn't it make sense that if it's even bigger, it must diverge? Now, this is the way you could use comparison test. You can't prove something diverges with a convergent function, and you can't prove something diverges with a convergent function. So you can only prove this way. If you have something that converges and you have something even smaller, If you've got a function that diverges and you've got something even bigger, So we already said 1 over x cubed, and I just want to kind of think about this. 1 over x squared converges. And 1 over x squared is greater than 1 over x cubed. And by greater, I should point out, at least on the interval that we're talking about. On the interval from 1 to infinity, 1 over x squared is greater than 1 over x cubed. So this must converge as well. And now I've thrown a little bit harder one in here. Okay, 1 plus e to the negative x over x. And 1 over x, remember, diverges. And 1 over x is smaller than this other function I've just given you. Now you say, well, how do you know it's smaller? Well, because I've added something in the numerator. If you start making the numerator bigger, which I have here, I've added a function to it. I'm making it bigger than it used to be, then I must be making the fraction bigger. So if 1 over x diverges and this is even bigger, then it must diverge. Now, this is a test that, as I said, is useful in some examples where you can look at something and right away say, oh, wait a second, you know what, that's going to diverge. It's not really even worth finding, finding the antiderivative and trying to put this in a limit statement. But this test is even more useful when we begin to look at series later on.